Hello everybody. Thank you. Thank you very much to all the speakers of this morning for the high level of each presentation. So we can continue now with the presentation of Comat with Luc Herrero and Antoine Blanchet. So I let Luc or Antoine begin their presentation. You have 30 minutes from now.
Okay, thank you, Alberto. So we are going to present our technology and development review about what we call plasma jetpack technology. And I propose a presentation in two parts. The first part, which is the introduction with global overview of company, product family, and the second part dedicated to technical achievement with Antoine Blanchet. So just a few words about our company. Comat is a 10 million turnover company with more than 100 people, and which is very important in Comat, it's that all the development cycle of a product is integrated on the same place. We have at the beginning of the cycle, we have the customer and market need analysis, technological development, you have design, manufacturing, assembly integration, and characterization at the end of the chain of the company. Yes.
Sorry to interrupt you, Luc. It is not a plain mode.
Not full screen.
Yes. Yeah, full screen.
Okay. Yes.
Please.
Yes. Yes.
Is it better like that?
Yes, it's perfect now. Yes, thank you.
Okay. So, okay. Which is very important for us is to have all subcontractors in Europe, in France, and to export our products. It's not only plasma jetpack, but all our products around the world. Okay, in US, China, Europe. So Comat begins these activities with International Space Station experiments, with microgravity experiment, biology, physical incubator, physical furnace, and we continue to have a manned flight experiment with a Thomas Pesquet flight last year, and we developed four experiments for this space flight, and for this year we have a blob experiment about a kind of mushroom growth in microgravity. We have a food processor things, and we have microwave development system in order to move particle in microgravity. So we work on legacy satellite equipment. We work on a military program with a pointing mechanism as antenna pointing mechanism for French government and French Space Agency. We work with meteorological satellites on a very high precision pointing mechanism for interferometer for science purpose, and we work on telecommunication satellite thermal regulation in order to master the extraction of power from payload to radiator, in order to be able to handle more data with this kind of satellite. And we work a lot on on-demand equipment for French agency, for European Space Agency, for Airbus, Thales, and now we want to work on off-the-shelf equipment, and that we are going to speak about. We have a different product line. We have reaction wheel ready for commercialization right now. We have plasma jetpack under development. We have a rotary actuator almost qualified, and we have antenna system. Antenna system are already available for commercialization, and we have a contract for Kinesis, for example, and for reaction wheel. We have already a commercial contract for 50 reaction wheel. For all our products, which is very important, is to develop building blocks in order to be able to create new products thanks building blocks and validated and qualified building blocks. These building blocks are based on industrial components, which is the cost, in order to have a very cheap and reliable equipment for space application. Which is very important for us when we perform a development. We try to follow as close as possible European ECSS, European Cooperation Space Standardizations. We try to have all our products with 8-year life duration in terms of electronic components. And to ensure the quality and competitivity, we have a complete manufacturing process adapted to this market to be competitive, and almost everything is done in-house in order to have a better quality and a better quantity for market needs and customers. So about the plasma jetpack, at the beginning of the project in 2015, we are looking for a propulsion module adapted to small satellites, and we try to find something which is safe. There is no issue with handle the system, to have very small volume system in order to make easier the accommodation of propulsion module on satellites, to a very low cost system. We do our best to have an environmental friendly development with no manufacturing constraints or feeding system. And we do our best to be ITAR free. So we are ITAR free with our products, and we want a product which is able to adapt to low power system. So we try to find something which is able to give 1 watt of power of thrust to up to 30 watts of thrust. So we are looking for all available physics in order to do as a kind of propulsion module, and we are focused on 2 physics. At the beginning, we work on a pulse plasma thruster based on Teflon, and now we work on vacuum arc thruster. And our technology plasma jetpack, it's a vacuum arc thruster with improved thrust to power ratio and specific impulse. So we call our technology plasma jetpack. So it's an electric propulsion module using solid metal propellant, as you know, for small satellites under 100 and 150 kilograms. And which is very interesting with this kind of technology, that it's possible to do different missions with this kind of technology because it's pulse plasma technology. We can perform orbit tracing, station keeping, deorbitation, and control altitude in certain cases, and direct compensation. Just a brief description about the physics. Okay, we expose criteria, and now we can expose physics. So the physics, we have a propellant here. It's a solid metal propellant, it's a cathode, which 0 volts at the 0 volts. And we have an anode at 250 volts. And at the beginning of process, we create an hotspot, and this hotspot emits electron flux. And this electron flux will vaporize the metal at the surface of the cathode. And this vaporization will create a metal vapor. And this metal vapor is ionized. So you have ionized metal by high speed. The metal vapor is ionized by high speed electron flux. And we have then in the process a very strength electric field due to electron cooling. This strength electric field creates an acceleration of ions in the direction of the outer space of the system. So here we have a quasi-neutral plasma, and we have very high-speed ions with very large spectrum of speed from a few kilometers a second up to 50 kilometers a second. So it's a pulse system. The picture is here just to say, okay, it's a pulse plasma thruster. It's not a continuous thruster. Here it's an old video that we have with a 10 Hertz pulse with a bismuth metal, for example. So we have the operation mode with a high-speed pulse, and you have unstationary plasma. Here we can have a look. And thanks to the pulse plasma thruster technology, we can modulate the thrust without any variation about the efficiency or so about specific impulse, for example. So yeah, we perform some analysis with French agency, and when we perform a zoom on the cathode, on the propellant, we can have a look on the different holes at the surface of the cathode, and these holes are cathode spots. So propellant is extracted from this hole they extract ions from this hole, and we have more and more holes we have a lot of holes during the discharge, and all these small holes define the erosion process of the cathodes. Here it's a typical cycle of the propulsion plasma jetpack system. At the beginning, we have a capacitor bank charge at 100 volts. We begin the process. At the beginning of the process, we have a ramp up of the current up to few kiloamps, and we have just a pickup thrust here, about 4 to 5 Newton, and we have high frequency noise on the main waveform of a current, and this high frequency noise are the arc which go from one spot to another spot with high speed. During one discharge of capacitor banks, about 5 joules, we have 1,000 or 10,000 of hectons on the cathode. And 1 hecton is holes on the cathode. So this technology is a little bit tricky because the efficiency depends on the cathode materials. So we try aluminum, titanium, tungsten, depends on the magnetic field topology in order to optimize thrust. So thanks to magnetic nozzle, depends of the current waveform here, and depends of the discharge chamber geometry. So there's 4 parameters will directly define the efficiency, thrust and thrust to power ratio, and specific impulse of the system. In our proposition, we have different products. We have 2 products. We have the first one, which is a plasma jetpack 31. The second one is the 80 watts. And to pass from one product to another one, we have just to duplicate validated building blocks. For example, for plasma jetpack 80 watts, we have more discharge chamber. We have 2 plasma generator units. We have 2 power propulsion supply and control units. We have just to perform a duplication in order to pass from one product to another one, and we have to adapt the discharge chamber to the new total impulse. Okay, in order to perform this development, we have an experimental approach because there is no very little literature about this subject. So we have to perform different experiments in order to have a better understanding about physics, about erosion, about technology behavior, thrust, specific impulse. So we perform 7 to 8 breadboard models. And we have different in-flight demonstration. We have an in-flight demonstration with our partner in China. We have in-flight demonstration with the CNES and European Space Agency and European Union in 2022, based on the 6U ISIS satellites. We will deliver this satellite next month, this propulsion next month, which is very important here to understand that we have no theoretical approach in order to perform modeling or something like that. And we have to perform to have an experimental process and very agile experimental process to improve performances of this system. So you have just 2 products here. I will not give more detail, but we have 2 products. The first one is plasma jetpack 30 watts, which is in a flat configuration. So it's 10 by 20 by 5 centimeters with a high specific impulse with 2,000 seconds. We have a mass of less than 2 kilograms and with objective of 4,000 Newton second. We have few advantages with this technology. We have solid metal propellant. We have on-demand thrust. We have no heating required. We have vectorized thrust. You can perform a vectorization of the trust as function of mission requirements. We can adjust trust as function of frequency. And we can adapt geometry thanks to building blocks to a customer requirement. If they need different shape or cluster or something like that, it's possible to perform a very quick adaptation. Okay, for this slide. So we have the second product, which is Plasma Jetpack 80 watts. There is a same trust to power ratio, but we want to improve total impulse up to 12 kilonewton second in order to be able to answer to to bigger satellites needs in order to have a larger market for this technology. So it's the end of my presentation. I will let Antoine present this part. Antoine, are you here?
Yeah, thanks.
Yes.
Can you close your presentation?
Yes. It's okay. I think you can perform presentation.
Yeah. Okay. Good afternoon, everyone. I hope you can hear me well. And now I will talk about the technical development and the latest achievement on the Plasma Jetpack. So as Luc said previously, we have an experimental approach to develop the product. But we have in 2020 a lack of information and knowledge about the vacuum arc physics. So in the frame of H2020 program, we start a consortium with different companies, laboratories, and startups who can help us to improve our knowledge about the vacuum arc physics, pull the facilities together, and also evaluate the impact of magnetic nozzle on the plasma parameters and performances. And one of the main objectives of this project is to have, at the end, a predictive model of the plasma expansion in order to design and optimize the Plasma Jetpack for the next product. So at the beginning of the project, we define the objectives and the targets for each partners. And the main focus is on the ion speed, the ion mean charge and electron properties. But we also have some measurements plane about the macroparticle tracking and the cathode spot motion. Obviously, we have to feed plasma solve in order to build a predictive model for the end of the project. So for that, at Comet we produce 3 thruster, 3 breadboard dedicated to this project. And the objective is to have the same configuration of the thruster to be able to compare easily the results from each other. So the first main achievement on this project is about the ion velocity. This morning we seen the presentation of Etienne Michaud, and this is quite complicated, in fact, to measure mean ion velocity, because we have a vacuum arc with high current and very short pulse duration, like few microseconds and few kiloamps. So it is important for this measurement to reduce the noise produced by the discharge itself, and be capable to record the signal on the recorder. So the main focus are on the grids and the time of flight method. And we find that all the partners have the same results. So we study different cathode material, brass, titanium, and nickel chromium. And we measure all the partners around 20 and 50 kilometers per second of mean ion velocity. So it's quite high compared to the other vacuum arc thruster in the literature. And we can see on the screen the two graphs presenting the current received by the probe as function of time in microseconds. And these currents are, in fact, the sum of multi-charged ions, at least 3. And it is complicated to have the mean ion velocity, because there is several spikes on the ion current. And we can only give the ion velocities of the population, respectively, of each spikes. So this is the plots of ICAR laboratory. So we can see here the velocity for titanium for 2 populations. The first one is a multi-charged one. So we have the highest velocity, around 40 kilometers per second. And the second one much lower at 30 kilometers per second. And we have a ratio that indicates 2+ and 3+ ion population for this. So the next step for the ion velocity is to have in parallel the mean ion charge in order to know more precisely what population are emitted by the plasma jetpack and at each velocity. Yes. So after that, we perform a thrust test and mapping of the plasma parameter with magnetic nozzle. So we build a coil around the thruster head, and we develop a dedicated electronic boards to drive the magnetic coil. So we have a huge capacitor bank here, about 900 microfarad. And we close the gate of a MOSFET in the closed circuit. So we discharge the high capacitor bank in the magnetic coil. And after that, thanks to a microcontroller, we ignite the vacuum arc of the plasma jetpack after a chosen delay. So by changing the delay between the main discharge of the magnetic coil and the plasma pulse, we can firing where we want on the blue curve. So we can choose the magnetic field that we want, and we consider that in the pulse duration of few microseconds, the magnetic field is constant. So first, visually, so we have here a picture of the plasma for different magnetic field. So we can see clearly a constriction of the plasma. More the magnetic field is higher, and that we have an impact on the plume by the magnetic field. So after we try to measure the thrust, the impulse bit of each plasma pulses, thanks to our thrust bench. So in this breadboard, we have drawback of dispersion for pulse to pulse. So we have here, even for without magnetic field, huge dispersion on the impulse bit. But we can clearly see an increase of the thrust as function of the magnetic field. And here is for brass cathode, we have an optimum about 80 millitesla. So after that, we try to understand why the thruster is higher with magnetic field. So we measure the plasma density as function of the angle. So we used ion flux probe at 22 centimeters from the thruster exhaust, and we sweep the angle from 0 to 90 degrees. And
Antoine, you have 4 minutes.
Okay, thanks. We plot this graph. So we have here the charge received by the probe, the ion charge. So the integral of the current as function of the angle. And we can see that we have a drastic increase of the charge with magnetic nozzle. So there is two hypotheses for that. The first one is that the ion is mean charge is higher with magnetic nozzle. And the other is that we have higher ion erosion and ion conversion with magnetic nozzle. So here is the plots of the ion density as function of time. So we can clearly see that we have more focalization with magnetic field. And so to conclude about this, we have an increase of thrust, also an increase of ion velocity in the axis, and a reduction of the cone angle of the plasma jet. So it's very interesting for us, this magnetic nozzle, because we can handle also the problematic of pollution for the satellite. So here is the same test, but not using a coil, but a permanent magnet. And we also have the same results, that we have an increase of the ion velocity in the axis with permanent magnet. So now we try to understand why we have this acceleration in the axis with magnetic nozzle, and also have a solid predictive model based on the classic plasma equation. So this is the work of PlasmaSolve in the project. The next part of the project is focused at COMAT on total impulse. So the total impulse is it's a most important parameters from us, because it drives the capacity to erode propellant. So we are now at 22 Newton second, and the goal is to reach 400 Newton second. So the main problematic is always the pollution of the insulators and the chambers after several 100,000 pulses. And for that, we have two strategies: passive cathode mechanism with mobile cathode, and keep also static cathodes, but with smart electronics, in order to erode a large amount of propellant. So for that, we have a concept generation process. So we have an idea, we design and manufacture it. We characterize entirely the breadboard, and we have after that brainstorming about the failure analysis after the next idea. So here, for example, a lot of breadboards that we test this year to understand how the erosion process takes place on the vacuum arc. And we continue to learn about this today. So in order to reach the main objective for the first product, to have 400 Newton second. And I have to go fast for the end. We develop also in parallel a plasma jetpack for ESA and Easy Space in the frame of in-orbit demonstration mission. So the main purpose of this mission is for us to have a software validation protocol in flight, and to have thrust estimation and PGP status monitoring, so temperature and pulse count. So you can see here the platform, 6U platform of Easy Space. And
Antoine,
here,
you have 2 more minutes.
Yeah, thanks. Here is the plasma jetpack. So in flight, we plan to perform a sequence, a firing sequence defined here. So we will place it at 13 watts, and we will run the thruster 30 minutes per orbit. And we plan to perform at least 30 sequences 6 times in order to have a good estimation of the thrust in the space environment. So for that, we are currently still in the qualification acceptance campaign. So we passed the mechanical thermal performance in 7 tests, and we are now at the live test duration. So to conclude, you have here the performances and the characteristics of the plasma jetpack for ISIS. And so we have succeed to produce, manufacture, and test all embedded thruster in 1U and 1 kilogram, and with a classical command from US 485, and with this kind of performances. I don't know, Luc, if you want to conclude with your last slide.
If you want, okay, only one slide just to conclude. Let's go and continue. Oh, won't I share my slides? Okay. Okay, it will be very, very brief. Okay. Speak about everything with Antoine. Okay. Just to conclude, because we have no more time, we have different advantages of the technology, but it's on the slide. I will let the slide, there is no issue. So as conclusion, we have solid metal propellant. We have very high power conversion process with a pulse with more than 100 kilowatts. We have quite good efficient electrical to mechanical conversion for this kind of very low power application under 30 watts. The technology is quite simple. The physics is complex, but the technology is simple, and we have a standard manufacturing process and highly repeatable process. And our electronics is a basic concepts and have a pretty good result in terms of reliability. And we plan to have in orbit a demonstration in the mid of the next year. We have one, first orbit demonstration with China at the end of this year. And we will want to have a final product by the end of 2022 for our plasma jetpack 30 watts. Okay, thank you. If you have any question.
Thank you. Yes. Thank you very much, Luc Antoine. So now if there are questions, we can listen to the question. If there are some questions.
There is, I mean, on the question and answer list, there is one question from Daniel Perez Grande. So the question is a magnetic nozzle generated with permanent magnets or with a coil? And if it's the latter, does this have an enlarged impact on the overall thruster efficiency?
Yes, okay. So at the beginning, we want to use a coil, okay? And the coil, with our concept, coil have no impact of the thruster efficiency in terms of reduction, but we not succeed in improved thruster power with this kind of technology. And now we use dedicated permanent magnets to perform topology, magnetic topology. And with this topology, we succeed in improved thruster power and specific impulse of the system. Daniel, do not hesitate to say me if it's okay for the answer.
Yeah, and also we have a much more efficiency with magnet because we don't waste power consumption than with a coil. So this is more efficient for us.
Yes. And okay, hello, Christophe. One point, Alain, when you stay at total impulse in your 4 thruster pack, only available if. Oh, we are not. It's more question.
The question has been removed.
Yes, resolved. Yes, you're right, Christophe. We speak together this point.
Yes, Christophe.
Few times. Exactly.
I open the micro of Christophe.
Thank you. Do you hear me?
Yes.
Okay. So yes, of course, Luc, we already speak of that. Just to highlight that when you say 4,000 Newton second with your 4 thruster pack,
yes,
maybe for the user, he cannot get that.
Yes, yes.
To be highlighted because because it's a counterpart of your choice, or the fundamental choice of having a metallic propellant.
You're right.
You cannot share this propellant with the other thruster. So
yes.
This is a big mistake that people can make, is they forget the fact that it's not a unified propulsion system. It's an independent, unique thruster for each one of the four.
Yes. But I think it's possible to put a little bit more propellant by chamber. It's one thing that we try to have, because we have very high specific impulse, and to have perhaps a little margin, it's not a big deal in terms of mass, due to a very high specific impulse. You understand?
Yes, after it's a lifetime, of course. So
yes.
Okay.
It's okay. Yes.
My point.
Thanks.
Thank you.
Thank you. You have another questions?
Yes, there is also another question. Yes.
Yes. Another question. I know you show the result of the simulation briefly, but I want to ask if you could collaborate compared to you.
Okay.
Yes. Why not?
Yes.
Why?
Yes.
Let's go on. Sorry.
In the case of ISIS, I suppose. We already measure of the thrust on one model, and we will compare this measurement on ground with the results in flight. So we will use the GPS localization and the velocity of the spacecraft to compare the on-ground and in-flight measurement. Only for the thrust. For ISP, it's impossible because we cannot estimate at the end of the life duration the mass eroded, in fact.
Yes. Okay.
Okay, so I think that there is no more questions. So thank you very much to Komat.
Thank you.
Thank you very much for this very good and very rich presentation.
Thanks.
And so we can switch to James' presentation. James from University of Southampton. The title of James' presentation is CubeSat deorbiting all-printed propulsion system. So you can start when you are ready, and you have, as this morning, 15 minutes plus 5 minutes for questions.
Yeah, can I ask the previous presenter to stop sharing the screen, please?
Yes, Luc, please. Can you? Okay, thank you.
Yes, okay. You now can share your screen.
Yeah.
Okay, we see your. You can start.
Yeah, brilliant. Hello and good afternoon, everyone. My name is James Slett, and in this presentation, I'm going to be talking about the CubeDeAlps project. CubeDeAlps is an acronym for CubeSat Deorbiting All-Printed Propulsion System, and it's a collaboration between us working at the University of Southampton, our partners at INCRON, and our funders, the European Space Agency. In this presentation, I'm going to give a brief introduction to the system, how it's going to work on an operational perspective, as well as some of the system specifications that we are aiming to achieve. I'm going to then talk about how we are going to generate thrust on both a physical and electrical perspective. Then I'm going to show some of the ignition testing we've done in ambient and vacuum conditions. Moving on, I'm going to talk about how we plan on validating the performance of our system, and we have two methods through which we're going to use this. Finally, I'm going to summarize where we're at in the project and what we plan to do moving forward. So what is CubeDeAlps? CubeDeAlps is a small 0.2 unit system who would attach onto the side of a cube satellite. The sort of cube satellites that we're looking to attach to are between 1 and 3 units, with the potential of operating on larger satellites through further development. Once CubeDeAlps has been activated, it then begins the deorbiting procedure. It's important to note that throughout this presentation, that QPDAPS is only for deorbiting purposes and does not aim to provide precision attitude control. This system could be activated by a number of ways, the first of which would be either by receiving a signal from the ground or by not receiving a semi-continuous watchdog signal from the primary CubeSat bus. Having such a capability is important because despite much improvement in recent years, the dead-on-arrival failure rate of Cube satellites remains high at 25%. Therefore, it's important to have this integrated capability. In order to achieve this, we are looking at a number of key system specifications that are derived from an analysis of the literature of similar systems. We are looking at a thrust between 1 and 10 micronewtons. The reason for the disparity is because the amount of thrust that you produce is directly proportionate to the power, and so larger Cube satellites with more power would be able to produce those higher thrusts. We are looking at ISP of 300 seconds while maintaining a very low power of less than 2 watts. We are looking at a total impulse of 100 newton seconds. So another big part of QPDAPS is looking at precisely what effect implementing such a system to a CubeSat would have. Presented on the screen is an earlier work of some of our simulations looking at precisely this question. What you can see is a study ranging between 600 and 700 kilometers of altitude. Looking at 600 kilometers, we can see that without QPDAPS, the system would take 5 years to naturally decay. Implementing QPDAPS reduces this down to 3 years. The difference becomes much more significant when we look at the higher altitudes, looking at this case at 700 kilometers. So at 700 kilometers, it will take 27 years to naturally decay. Adding QPDAPS brings this down to 15 years. The reason why this number is important is because the 27 years is above the 25 years recommended guidance by the IADC. Therefore, without QPDAPS, a satellite operating at this altitude would be IADC incompliant, but becomes IADC compliant once the system has been attached. This expands the capability of Cube satellite operation and expanding their role within the Cube satellite economy. Another feature is, as indicated by the name, is that we plan on implementing printed technologies and printed capabilities into the framework of our system. This gives us a number of key advantages. The first of which is it allows us to rapidly prototype and manufacture models in-house. The sorts of things that we're looking at manufacturing using these printed technologies are electrical components within the power processing unit and the electrodes of the vacuum arc thruster itself that I'll be talking about in a future slide. What you can see on the screen is us manufacturing using dispenser printing an electrode pair in-house in the lab at Southampton using ink supplied to us by our partners over at Inkwell. Using this technology also allows us to directly implement the thruster into our PPU without the need for an additional interface. We're also able to customize the geometry, specifically when looking at producing the electrodes, as the cathode, which I'll explain later, is what provides the propellant and will allow us to customize for a particular orbit. It is also a low-cost way of doing things, which is important when looking at the Cube satellite economy. So how are we generating thrust? What you're about to see is similar in concept to what was explained in the previous presentation. The difference here being is that we are looking at a printed set of electrodes onto a substrate. We are looking here at a single electrode pair with a circular cathode in blue, surrounded by an anode in red, and a cross-section of which has been taken. There is a thin conductive layer connecting the two of them, which allows for triggerless operation. The vacuum arc thruster operates in pulse mode, and I'm now going to show what happens during a single pulse. At the start of a pulse, a high electric potential is applied between the anode and the cathode. This partially evaporates the thin conductive layer connecting the two. This provides a medium through which electrons can pass between the cathode and the anode in vacuum. These electrons pass in very high current densities, so at the base of which these electrons are being emitted from, the Joule heating is such that some of the cathode material is partly vaporized. Some of this vaporized material is ionized by that self-same stream of electrons and are then ejected from the cathode spot by a potential slump seen at the surface of the cathode. It's the ejection of these high velocity ions which provide the basis of the thrust for the vacuum arc thruster concept. Another key thing to point out is that some of these ions actually return back to the surface of the thruster, which replenish that thin conductive layer. This allows for continuous operation, and I have an excellent example to show you from our testing later on in this presentation. We've also developed our power processing unit through which we can power the system. What you can see on the screen is a direct output of our power processing unit, looking at both the input current and output voltage. The PPU operates on two phases, charging phase and the discharge phase. Simply put, during the charging phase, a capacitor is charged through an inductor. Once this current reaches a peak, this current is rapidly switched off, and this rapid change of current through the inductor provides the voltage required for that initial vaporization of the thin conductive layer. Subsequently, within the pulse, a much lower voltage of 25 volts is supplied by the capacitor as it's charging, which maintains the vacuum arc for the remainder of the pulse. Now I'm going to show you what this looks like when we attach this PPU to a printed electrode pair. What you can see here is a printed electrode operating in ambient conditions at 20 Hertz. The next video I'm going to show you is operating the same PPU at a much lower frequency, only we're operating in vacuum conditions. I'm aware it's not too clear what we are looking at here, what the electrodes look like, but I'm going to show you in more detail in the next slide. So what we saw in vacuum was this system firing. What we can see here is an image taken after several thousand ignitions of our PPU. So we're all on the same page on what we're looking at. Looking at the image on the right-hand side, sorry, on the left-hand side, we can see the cathode is a square copper block in the center. The anode is the thin bar at the top, and the thin conductive layer is the black substance that connects the two. There's two key findings I'd like to point out. The first of which is we can see where some of the copper material has been ablated and eroded away. Closer inspection can show craters where individual cathode spots are formed. The other key finding is where some of the ions have returned back to the surface of that thin conductive layer, tinting it in a slight copper color. This replenishment of the thin conductive layer has meant that under vacuum testing, we have not once encountered a situation where the inability of the thruster to ignite has been a limiting factor in our testing. With this successful, we then moved on to the next iteration of our system. This system comprises of two blocks of 25 thruster pixels. First block comprises of copper cathodes and the second block aluminium cathodes. The reason why we are selecting two separate materials here is because the performance of the vacuum arc thruster is heavily dependent upon the cathode material used. Different cathode materials have different ion velocities, different mass erosion rates, different ion state distributions, and by looking at this system and analysing its performance between the two, we'll be able to see an example of this literature in action. We have actually already produced several iterations of this model, and that's what you can see on the right-hand side of the screen. Similar to before, we have activated this system and powered it using our power processing unit in both ambient and vacuum conditions. As before, we are operating at 20 Hertz, and I'm going to show a video of this system operating at 20 Hertz in ambient conditions. We can see that the discharge location of the cathode pixels is shifting between different pixels independently. A good example of this can be shown in the long exposure image taken over several ignitions on the right-hand side. The difference here is this image is taken in vacuum. We can see that the primary discharge location is located in a single cathode pixel, but closer inspection indicates that smaller discharges are actually occurring at different cathode pixels. This gives us strong reason to believe that over an extended period of lifetime, as a single thruster pixel, as the cathode in a single thruster pixel is eroded, the primary discharge location will shift to a different cathode pixel as the separation between the anode and the cathode shifts, allowing us to not need to incorporate a dedicated switching circuit to control each of the pixels. So now we've achieved successful ignition. Our next stage is to be able to validate the performance of the MOT system. The key issue that we are running into is that because of the such low thrust levels, again, between 1 and 10 micronewtons, and the post-operation, it's very difficult to directly determine the thrust. Therefore, we plan on characterizing the system by measuring a number of key performance requirements through our collaboration with the European Space Agency. Through this collaboration, we have secured 1,000 hours of testing at their ESTEC facility, and we plan on using the literature produced by James Polk to be able to characterize and give a full indication of the performance of our system. Different parameters, as well as different ways that we plan on measuring them, are shown on the screen. The other way through which we plan on characterizing the performance is through a collaboration with the electric propulsion company Magdrive. Through this collaboration, we are going to supply one of the vacuum arc thruster systems that I was talking about earlier, and they're going to work on the power electronics of the system. Together, we have secured a 0.5U space in a 6-unit CubeSatellite bus. We've agreed with the satellite provider that once this has been launched, they're going to switch off the attitude control system, at which point we're going to measure the rotation rate and activate the thruster. After a set period of time, we are then going to
James, sorry, you have 2 minutes.
Yeah, okay, last couple of slides. Yeah, so once we we will then remeasure the rotation rate, and from that we'll be able to calculate the amount of impulse imparted at that location. As we know the mass distribution of the Cube satellite, we'll be able to then use this information to calculate the amount of impulse at that location and the thrust and the average thrust produced over a period of time. So in summary, the overall QPRs project is still at a low TRL, between TRL 2 and 3, and we aim to characterize the performance of our system of an all-printed propulsion system for deorbiting Cube satellites. We have a working breadboard model of our power processing unit and breadboard vacuum arc thruster. We have conducted ignition tests in ambient and vacuum conditions. We are set to begin performance characterization through experimentation and an in-orbit demonstration. Once characterization is complete, we can plan to continue development to produce an engineering model of the QPR system. Thank you very much for listening, everyone. Now I look forward to any questions that you might have.
Thank you very much, James. So there are some questions.
Yeah, I have some questions for you, James. Thank you for the presentation.
Mm-hmm.
My first question is, how do you ignite the main arc between the cathode and the anode?
So is that how we ignite the main, main point? So going back to the earlier slide, so again, we initially ignites through the triggerless operation of the vacuum arc thruster. So by having that thin conductive layer, it allows us to have some vaporized material, and that vaporized material provides the medium through which.
So what is the voltage? The voltage do you use for that?
We're up to 1 kilovolt for that, which we have measured from our power processing unit.
Okay. And what is the erosion of the substrates in Teflon compared to the cathode erosion?
So the sort of substrate that we're looking at using for this is plus 90% alumina. And looking at literature, you can operate several tens of thousands of ignitions, and there's not been a noticeable erosion of the substrate, providing we're using alumina, particularly at the relatively low overall power levels that we're using. So short answer, not very much.
Okay, thanks. And what is the number of pulses that you already perform and the energy per pulses, if you know that?
So the longest duration testing we've done is, could you move to, is on this system here. And this was, I believe, 5,000 pulses over a period of a couple of hours of testing.
Okay. 5,000. And do you know the energy per pulses?
These ones, I believe for these ones, for this PPU, it was 0.1 joules.
Okay, thanks. Perfect. Thank you, James.
You're welcome.
Okay, so there is a question from Gary. Gary, I opened your micro so you can speak directly with James.
Yep.
No,
you can speak if you want.
No, I think that Gary has a problem with his microphone.
Okay. Okay.
But I can read the question. He said, hello, I'm sorry if I missed the information, but how can you ensure that the thrust direction is achieved during the months of thrust needed to deorbit a 1U CubeSat from more than a 500 kilometer altitude with several tenths of micronewton?
Yeah, so that's one of the issues that we're facing. So again, looking at a lot of the work that we're doing in the size of analyzing the performance is looking at how exactly we can overcome this issue. And what we plan on doing is being able to modulate exactly when we fire. So although there will be a rotation within the satellite, our kind of plan is to only activate the vacuum arc thrust system when it is pointing in the correct direction. And that direction would be to deorbit the Cube satellite.
And he asks also, what are the requirements on the attitude control system? Continue, especially if the thruster is turned on because the satellite is not responding after launch.
So to clarify, so you're asking what the requirements are on the attitude control system such that we'll be able to determine what direction would be we would need to fire. So we would need to. So we need to be able to know. We don't need to know precisely which phase is in, like, to the degree, but we would need to know within that we're in ±5 degrees is what we're currently looking at, and that's what our assumptions are based off of for the simulations.
Thank you.
So a lot of our simulations do take into account the fact that we'll be rotating and we'll be activating the thruster when it's not precisely perpendicular to the direction of motion.
I think that Christopher also has a question. Maybe we can give him the microphone.
Yes, thank you for your presentation, James. But I do not understand how you can control the thrust vector with such matrix. It is very important for OCS attitude control system to know where is the thrust, which direction. With the matrix, okay, it's quite large.
Yes, so again, so we're not looking at using the system to actually precisely control the attitude. So if you imagine that matrix being expanded out over the whole unit of the Cube satellite, we expect that there will be some induced rotation as the primary discharge is located at a single pixel, but then extrapolated over the full duration of the satellite, this would then be dominantly cancelled out. So it's not that we will be continuing to precisely control the attitude. We will be only firing at the point at which the thruster is pointed in the appropriate direction for deorbiting purposes.
But you will induce attitude movement, and so you may produce a spin on the satellite, or flat spin.
And so I'm going to hand over to my colleague who is working more precisely answering these sorts of questions.
Yes, so of course, because of the grid formation of the thruster, whenever we ignite a single pixel, there will be some motion induced in the attitude of the CubeSat. However, what we can do, for example, we are looking actually currently at the different methods where we could ignite the thruster to make sure that we actually do not destabilize the attitude of the CubeSat by too much. The method that we have found that works quite well for the moment is by using an open loop control system to ignite thruster heads, but are symmetrically opposite of each other on the same CubeSat base. So that once the pixel has been fired, another one will counter out the rotation that has been previously induced. Does that kind of make sense to you?
Yes, sure. That would be much better. Thank you.
You're welcome.
So thank you very much. So we finished time. So thank you, James. Thank you for this very, very good presentation.
Thank you very much.
Thank you. So we can switch to the next presentation. Presentation from University of GSN in Germany. The title of the presentation is Characterization of the emission behavior of internally weighted electrospray emitters fabricated via 3D microlithography. So Finn, if it's okay for you, you can start when you are ready, and you have 15 minutes.
Hello and welcome. Can you see my slides and can you hear me?
Yes, yes. We can see your screen and we hear you very well.
Very well, then welcome from me. My name is Finn Kunze. I'm part of the Electric Propulsion Research Group at the University of Gießen, Germany. And I mostly do research in the regards of electrospray emitters for space applications, and especially microprinted 3D electrospray emitters used with ionic liquids. And I will walk you through my presentation. I will first motivate why we are researching electrospray emitters. And electrospray emitters are inherently small. We're talking about sizes of 100 micrometers and downwards. Especially what we are researching go down to like 10 microns in the capillary orifice, and they are ideal for CubeSats. They may provide very low thrust, but for station keeping and other purposes, they are very good. Also, they use readily accessible alternative propellants, mostly commonly ionic liquid and liquid metals compared to gaseous propellants like xenon. They are much cheaper and they come pre-ionized if you're talking about ionic liquids, and liquid metals are easily ionized with a static field. So we can make these propellants work very easily. Furthermore, the electrospray emitters have a high electrical efficiency. They have low operating voltages. We have very little heat that is generated. And if you use ionic liquids, we have no need for an external neutralizer, as we can operate them in both polarities and have a self-neutralizing propellant system. Applications would be, for example, deorbiting and station keeping. As I said before, the thrust overall is not very high, but for constant thrusts or impulse bits, they are very well suited. I want to shortly explain the working concept of electrospray emitters. Generally, there are three types: externally wetted, porous, and internally wetted capillary type emitters. These three types differ primarily in their way how the propellant is supplied to the extraction site. And I will explain the working principle for an internally wetted capillary type emitter shown on the left-hand side as an example, as the work principle is very similar. Generally, you have a static electric field interacting with a propellant. And I will show that here we have a propellant which is supplied via a capillary to an extraction site, where at the extraction site, the fluid is exposed to an electric field provided by an extraction electrode placed near the emitter tip. Due to the electrical field, the fluid meniscus is deformed, forms a so-called Taylor cone, named after the researcher who found it. At the tip of the Taylor cone, ions generally are exposed to very high local electrical fields, which may lead them to overcome the surface tension and exit the fluid, forming an ion spray, which then can be used to generate thrust, or in other applications are used as mass spectrometry spray, carrying other parts that are interesting for mass spectrometry. And if you place a secondary acceleration electrode behind that, you can also control very well the speed or the further accelerate the ions for space applications and thrust generation. Before I dive into the emitters we processed, I want to first talk about the fabrication process. We're using 3D micro laser lithography as means of fabrication. 3D laser lithography is an additive manufacturing technique with a broad choice of available polymers, in our case, photopolymers, which may be supplied by any kind of photolithography manufacturer, as they are most commonly known for fabricating electronics. It's an advanced 3D printing on a microscale technique, which inherits most benefits from 3D printing, such as freedom of design. We also have a high resolution at the micrometer scale. I've shown two test structures provided via this technique. As you can see, the scales may be a little bit small on the bottom hand side, but we're talking about scales on the micrometer scale. And the detail grade is very high, even for structures like these fractals, finally fractal on the bottom hand. Furthermore, we can process STL files, which are compatible with any kind of 3D modeling software or CAD software for engineering purposes. Or we can use program code to define a laser path. And I will talk a little bit about that later. So how does it work? The general workflow for 3D microlithography is you provide a substrate. And on the substrate, the photopolymer, which is used as material, is pre-deposited. Then you have a near-infrared laser with photon energies too small to trigger a photoreaction in the chosen photoresist. We focus this laser through a microscope optics down to a very small point. And at this point, this focus of this optics, two photon processes occur at a sufficiently high rate. So we can say we have, statistically speaking, a guarantee for two photon processes to occur. And if two photons are absorbed from the photoresist, the energy is high enough to trigger a photoreaction and curing the photopolymer. And the exposure only is affected in the small volumetric pixel, so-called voxel, around the focus point. And by moving this voxel around inside the photoresist, we can basically generate any kind of structure we want, provided we use negative tone resist, which means the photoresist is hardened if it's exposed to light. And I want to show some results we fabricated. These are our microemitters. On the left-hand picture, you can see a single microemitter with a capillary diameter of approximately 10 micrometers, placed on a handling base, which allows us to handle the emitter itself, as it's very small. We're talking about emitter sizes in the single or double-digit micrometer range. Handling it with tweezers is very hard, so it's placed on a base plate we can handle. Furthermore, we can use this technique to fabricate identical emitters into an emitter array. An example array of 5x5 emitters is shown in the height-end picture. As you can see, the emitters are identical and the fabrication quality is very high. So there are no major defects between single emitters. Furthermore, if you have a look at the capillary orifice and the capillary pathway, on the left-hand side, an SEM picture shows the bottom side of the opening of the capillary orifice. And you can see even at the bottom side where you would expect some defects, the capillary is well defined. And easily readable that the diameter of the capillary is about 10 micrometers. And on the right-hand side, I've cut away material using a focused ion beam, revealing the internally capillary of the emitter. As you can see, the capillary pathway is also well defined, and there are no deformations, or the capillary is very consistent in its width along the whole emitter. So there are no hindrances or something that could impact the fluid passing through the emitter. And now we have emitters, and we want to characterize the emission behavior, because that's the primary reason we're fabricating those emitters. And here's a schematic shown which depicts our setup we're currently using. We have the emitter placed here on an holder. The emitter is glued to the peak holder, carrying a capillary and sealing the fluid, so that any ionic liquid which is passed through the holder only exits through the capillary orifice. Then we have an extraction electrode placed near the emitter. We're currently using an external electrode, so that means the electrode is not yet integrated into the emitter itself, and a collector plate for the data acquisition. The data is, you analyze the voltage signal from the collector plate using an amplifier electronics, which translates incoming charge into a readable voltage signal, which then is saved by an oscilloscope or a multimeter by a PC. The fluid is provided with a high precision syringe pump, where we can choose the flow rates of the propellant up to down to some nanoliters per minute. So very low flow rates are possible if needed. Furthermore, if we use the Bradbury-Nielsen gate placed between, we have the possibility of achieving time of flight measurements. And here are some of our results. These are preliminary results, as the research is still going on. I can sadly show you only some data we could acquire. This is a peak acquired with an oscilloscope using a single triggering mode. We presume that this is a single droplet hitting the collector plate. On the right-hand side, you can see some impacts on the collector plate on a very small magnitude, with only extraction currents in this picoampere rate, presumably a very fine spray hitting the detector. Unfortunately, our current characterization setup is not up to the task. The time resolution of the DC measurements is insufficient. We have a lot of propellant use, but not a lot of signal generated on the detector. So we presume that we have a lot of loss due to the time resolution, as the oscilloscope shows multiple impacts, but the DC measurements don't. So we also sadly could not acquire time of flight data, as the duty cycle is even lower and time resolution needed for current measurements are even higher. Therefore, we improve our detector setup in the upcoming month. We upgrade to a multi-channel plate high-resolution detector for mass spectrometry purposes. This gives us axial resolution due to the delay line detector, allowing us to measure the plumb angle, and also mass information becomes available, and velocity information of the ions extracted. Therefore, I come to my conclusion. What we've done so far, we've shown that the fabrication with 3D lithography is possible, and we can achieve the production of emitters in a single process flow. We have a very high resolution and print quality, even on the micrometer scale, and we can fabricate emitters very easily. Furthermore, we have well-defined capillaries, even at low diameters. The first measurements show promising results, with the possible upgrade on the way, and we hope to present better results in upcoming conferences and papers. our outlook, we want to integrate the extraction electrode into the emitter array itself, therefore eliminating the need for an extraction electrode placed near the emitter and also reducing the size of the whole emitter extraction electrode compound. Furthermore, reducing the needed voltage to achieve a stable extraction. And we want to make more research on using the freedom of design available to us through the 3D printing technology, generating, for example, zigzag capillaries and tailoring the emitters to the need of the fluid hydraulic resistance and the extraction rate, etc. And thank you for your attention. If there are any questions, be free to ask.
Thank you very much, Finn. So now if there are some questions, it's the moment. Okay, so we have a first question. The first question is, how long is the process?
The whole process from the coating of the wafer used till the product is finished is about 12 hours. And most of the time is for the exposure and is automatically done by the device we're using. So 12 hours, you got your emitter array.
Okay, 12 hours. Thank you very much. And we have also how dedicated these structures are to atomic oxygen.
That is hard to answer, as we want to put these emitters in a special test chamber, which simulates the harshness of low Earth orbit with a plasma and also atomic oxygen. So I sadly cannot answer the question with certainty, but I'm pretty sure they are relatively resistant to atomic oxygen. The photopolymer used is also known as one of the hardest materials in lithography applications and is very resilient on a chemical and mechanical level.
Okay, thank you very much. So we have another question. Do you see degradation of the cone tips after some emission?
Currently, no. There is the possibility for arcing, so an electric arc hitting the emitter, then the emitter itself will be most commonly completely gone. But it's not really degradation of the emitter tips itself. It's more a problem if you have too much residual gas. So degradation seen yet, no. Possible destruction, yes.
Okay, thank you very much. I think that this was the last question, maybe. Okay, so thank you very much, Finn, for your presentation.
Thank you very much as well for organizing this workshop.
Thank you. So we can now switch to the next presentation, Tony's presentation from Impulsion, Austria. The title of the presentation is Flight Heritage Fit Propulsion Systems for Small Satellite Missions. So welcome, Tony. When you are ready, you can start, and you have 15 minutes.
Yeah, good afternoon, everyone, or whatever time it is where you are. I'm filling in for my colleague, David Krejci, who unfortunately had to cancel on a short notice. So I will be presenting today Impulsion's work on flight heritage feed propulsion systems for small satellite missions, and which is in the framework of this FEEP session. So at the core of our thrusters of our technology lies the FEEP aspect, and in the very center of our thrusters, we have our emitter that is a circular array of 28 needles. And due to its shape, it was dubbed the crown emitter. And it consists of porous needles of tungsten material that form or that are filled with liquid metal propellant. So they're wetted in a dedicated process to accumulate the propellant inside. And then by application of a high potential difference between the emitter and an extractor electrode, we have the same principle as was described just now, with forming a Taylor cone, and then due to the field emission, we extract the ions and accelerate them in order to create our ion beam. The technology behind the thruster product that we are selling and producing predates the company and was actually developed with our research partner FUTEC, which was previously a part of the Austrian Institute of Technology. And the FEEP technology was developed there for about more than 25 years for scientific missions with a strong support through the European Space Agency and through other third-party funding. And originally it was designed as a liquid metal ion source. There, as also previously mentioned, as part of a mass spectrometer experiments on the Mir space station. Later it was used for potential control of spacecrafts, sorry about that, including famous missions like MMS, and then also on a mass spectrometer experiment on Rosetta. And because the liquid metal ion sources were such a success in these flight missions, they were then further developed into an actual use as a propulsion system, because if you have the ion emission mastered, you can then scale it up in order to create thrust necessary. So at the core, as I said, is the ion emitter, which is soaked with the propellant, which will be solid during launch and integration. So it's very easy also for spacecraft integrators to handle. It's safe for debris because the propellant is not hazardous. It's not pressurized. Again, makes it very easy for integration and handling. Non-toxic, nothing related to reach. So that all makes it nice and easy. And I don't know why this is moving, but okay. And the ion emitter itself was validated in an ongoing endurance test. We're always updating this slide because it's surpassed already 30,000 hours. So you see that this slide has been used already for quite some time already, which is much larger than the total impulse that we would see at nominal thrust in the thruster that we designed around the emitter, which shows how robust the emitter technology itself is in terms of lifetime. So from the two, from the emitter technology, we built a thruster around it. So on the left, you see our heritage product, which used to be called the IFM Nano Thruster, which is just now called the Nano for short. So it has the emitter, which in our case needs to be neutralized. So we have two neutralizers available for the neutralization effect. The emitter itself also hosts the propellant tank. So it is filled with the solid metal propellant and a heater to heat it up in order to liquefy it in flight. And then we have the electronics at the bottom to apply the high voltages required to initiate the potential difference and also to heat up the propellant tank and the neutralizers. And then in a more later development stage, when the Nano was already flying and being mass produced. We built the IFM micro thruster, which is called now the Micro R3, which now hosts 4 of these ion emitters, and then some more neutralizers to accommodate for the lifetime requirement. Larger propellant tanks, but based on the same principles of heating the propellant reservoir and then having a power processing unit in this box underneath. The arrow is a bit wrong, but it should go to the box to host the electronics. And then when we start emitting ions, we see this characteristic blue light, not as shiny and beautiful as much other plasma thrusters, but as such efficient as it does not lose too much energy in the plume. And for the micro on the right hand side, we have the 4 emission sites, then basically all operating together to create more thrust, and as such being more suitable for larger satellites. So as I said, we are producing the Nano now on a large scale, which everyone eventually also wants to see in space. So over the years, what you see plotted here is the number of thrusters in orbit. So we had a in orbit demonstration on a commercial flight Easter 2018. Sorry, I don't know why it's moving. And after a little bit of while, we saw that the numbers is climbing as more and more customers managed to get their satellites into space. And we had a quite large jump recently in midsummer with 25 nanothrusters on a single flight across various satellites of various customers, which was very exciting time for our flight support department, obviously. And we have now 87 nanos in orbit, so we're reaching soon the 100th thruster in space. And we have more than 200 thrusters delivered, so there's certainly a backlog of satellites going into space with our thrusters. So to talk about the very first mission, we had independent verification of the thrust generation in space as well, by measuring the change of the orbital parameters. It was a 3U CubeSat, so there you actually see quite a strong change in orbital parameters by the thrust, which was also reported previously, where we saw that the indirect thrust measurement from telemetry fits very well the measurements from GPS. The indirect thrust measurement was also validated by means of a thrust campaign at the Electric Propulsion Facility at ESA and ESTEC, where we also saw that there's quite a good agreement between measurement and modeled value. From the flight missions, we got obviously telemetry as much as customers are willing to share with us, where we can also then verify the temperatures during thrusting times. We can see the power demands and consumptions in flight, just to then cross-check with terrestrial data, and then see whether there are any changes in operation in flight compared to the ground. And we could also see that, well, we did see thrust as we expected, so we reached nominal thrust levels as well. And then 1 year after the commissioning of the first flight, we also ran different tests in order to see whether the command granularity is achieved. So running different thrust steps in order to really see that we get to the thrust that we want to command, which was reproducible and show that we really have a robust system even after a year in orbit. As we said, we do need neutralization. So some things that customers are very eager to see is also that actually we do neutralize our beam and not to cause any issues on a satellite with a potential buildup. So we have thermionic filament neutralizers that we verify on ground. So we have a collector inside of our vacuum chambers to then measure all the currents in question and then compare them with our measured values inside of the PPU in order to then see, okay, well, the green line here is the one you need to look at, basically saying, okay, there is no current in either positive or negative direction leading to a potential buildup. And we do that for every thruster as part of the acceptance test in order to prove that there's no issue with the neutralization. And then we run these tests with the neutralization also against different thrust operational points in order to see whether there are any operational envelope points that are not allowed. So as long as these black line stays below 0, we basically have margin for neutralization. So as part of the performance acceptance testing, we run the green thrust here up in order to see whether it would run any issue. And as we can derive from the plot is that at the nominal thrust level of 350 micronewton, we are still below the line in the neutralization, meaning that we have a success there, satellite. So much for the heritage. Obviously, we're working on the future as well. So we're developing a new generation of thrusters based still on the same principles and technology. So here's the portfolio lineup as of now. So we have the Heritage Nano with the characteristics that you see below. We have a threefold generation that is following the Nano.
Tony, sorry, you have 2 minutes.
Sure, thank you. Which is called the R3, AR3, and IR3, with the R3 being a direct development, of the Nano, whereas the IR3 has a slightly higher thrust operational point at the expense of ISP. So it's just shifting a little bit the characteristics there, and the AR3, which I will show slightly later, will then also introduce thrust vectoring capability. And then, as I said, we also have the micro with the higher thrust potential. So the R3 is built on the same technology in terms of the crown. So the emitter is actually exactly the same as it is on the Heritage. But we made quite some changes in the PPU design in order to be more radiation tolerant, to be more robust in terms of reliability, architectural changes, firmware changes, in order to just increase reliability and robustness to the space environment. And then we also learned from what we've seen with the flight integration on the several customers, and in order to mitigate some of the risks there, we changed a few aspects in the mechanical and thermal interface to help customer integration. And for the AR3, as I said, you see here that the extractor is split into 3 different segments, which will then allow for a vectoring capability based on a potential throttling of these extractor segments to shape the electric field in a way that the ion beam is then vectored to our wishing. The R3 is currently undergoing qualification in the frame of an ESA project. So several qualification models have been built. They went through environmental testing, and we're preparing for lifetime testing there as well. So far, everything is nominal, and you see the QM on the left there. The AR3, as I said, with the thrust vector throttling, we tested on engineering models to see whether the throttling or the directional steering of the beam is working. So what you see on the left-hand side is basically the same emitter, just in different states of electrical parameters. And as you can see,
30 seconds, Tony.
Yes, and as you can see from the needles, we steer in different directions, so we can get a complete picture of our thrust inclination wherever we want. Then going briefly over the micro, we also had the first flight of the micro in space, commissioned with an orbit change maneuver. We have a press release if you want to look a little bit further there. But flight mission wise, we see the same data in telemetry. Everything satisfactory to the point we created thrust in space. We could change the orbit, and also proves that the micro is working accordingly, which brings me to the conclusion that you can read here. So we have new things, new arrows in the quiver, and then hopefully we see more of those going into space then as well soon, with the R3s lining up for our customers already. Yeah. That brings me to the end. Thank you very much for listening in.
Thank you, Tony. Thank you very much. So we have, I start with question. We have a first question. Do you plan to invest in some other form of electric propulsion?
Not at the moment, since we have the heritage and the production capabilities for FEEP. I think there's still many ideas on what we can do with FEEP technology first. So for now, we are sticking with that. It's been on the discussion table a few times, but as of now, we're sticking with FEEP.
Thank you. So maybe one or two more questions, if we have them.
I see our colleagues from Gießen have a question there. He's raising his hand.
Yes. Yes.
So can you hear me?
Yes.
Okay, thank you. May I ask the question if you ever used ionic liquids or other kind of self-neutralizing or possibly self-neutralizing propellant?
We haven't done so in the company. There had been investigations at Fotec, our research partner, to check for alternative propellants, mostly there for alternative liquid metal propellants, because that's where their expertise is. I know they've looked into ionic liquids, but as far as I know, there was no test anytime recent that I would know of. And David, who worked before coming here on electrospray thrusters, has experience with ionic liquids. But as far as I know, there was not any advantage really at the moment that would justify the change in propellant.
Okay, thank you.
Any other question?
Yes, there is one question from Christophe. Could you remember us what is the efficiency of a thruster? Jet power divided by input power.
From the top of my head, I don't have a number available. No, I would have to calculate. I don't have it in my head, sorry. But I mean, if you look up the performance parameters, you can basically calculate by yourself. So you have the thrust, the specific impulse, and the power if you want. So I believe you can do the math.
Yes, between 10 and 20%.
Okay. So maybe a last question. There seem to be several images where several of the emitter tips do not work, notably on the microwave free firing picture. If this happens in space, are you concerned at all about unwanted torque on the craft, or has this problem been dealt with at this point?
So yes, indeed, there are sometimes occasions where some needles are not firing. Sorry, sorry, go slowly. I believe you mean this picture. So the picture itself is from an earlier stage of the development of the micro, where I mean it's still development stage, and there's a constant improvement on the emitter quality in production, and we're now at a stage where we get maybe 1 or 2 needles not firing, but typically we see a full needle crown firing. So that would imply then the torque is not induced as much. And obviously we try to fulfill customer requirements as much as possible. So if a mission requires a very strong pointing accuracy or very little thrust vector offset, we will select emitters that are better in quality as a result of the production process, in order to fulfill these requirements. So the luxury of having a mass production is that you can swap things around to your liking. So we have emitters checked and characterized as part of the what we call a burning characterization, and then based on the characteristics, we will assign these emitters to certain thrusters. So for some customer, this offset might not be a problem if they have either good magneto-torquers or any other good EOCS capabilities. Whereas for some missions, certainly customers would be very concerned if the offset is too large. So then there's really what is really required for the customer is taken into consideration in production.
Okay, thank you very much, Tony. Thank you for your presentation. And now we can switch to the last presentation of this session, the Matthew's presentation from Space Propulsion Laboratory, the Massachusetts Institute of Technology, MIT, US. The title of the presentation is Ultra-Dense Ion Electrospray Microthrusters. So, Matthew, when you are ready, you can start. We have 15 minutes plus 5 minutes for questions.
Okay, thank you. Hi everyone. My name is Matt Corrado. I am a graduate student at MIT in the Space Propulsion Laboratory, advised by Professor Paolo Lozano. Together, this project is a collaboration between the Space Propulsion Laboratory at MIT campus, as well as MIT Lincoln Laboratory and the US government. And special thanks to those who have helped me specifically with this presentation, who aren't here currently, but Lolita Paraswarman and Melissa Smith from Lincoln Laboratory and Paolo Lozano at MIT, as well as a bunch of other people working on this project at both institutions. So the topic of this talk is an ultra dense version of an ion electrospray microthruster. And I will go into a lot more detail on that coming up. So first of all, I just want to go into a little bit of detail about ion electrospray propulsion in general. I know that many people may be familiar with this, so I'll be relatively brief, but a few things that I certainly want to highlight. So first is that electrospray thrusters, much like other types of electric propulsion for satellites, use electric fields to accelerate ions. And those ions accelerated produce thrust. So the difference really between electrospray propulsion and other types of electric propulsion is really in the mechanism through which those ions are produced. So usually with electrospray ion emitters, they take advantage of some kind of microfluidic process to move an ion-rich liquid, sometimes ionic liquids, in the case of this project in particular, and move those liquids to a sharp tip where a meniscus is allowed to form, and a strong electric field applied at that point sharpens the liquid at that meniscus until it becomes sharp enough where the local electric field is very large, so tens to hundreds of millions of volts per meter, at which point an instability will arise and ions will evaporate directly from that surface. Those ions are then accelerated through a potential difference applied between that liquid surface and a downstream extractor electrode. So the scale of these emitter tips are very small, so like hundreds of microns. And since no dedicated volume is needed for ionization of the propellant, these electrospray thrusters tend to be extremely mass and volume efficient, compared to other types of propulsion. And in addition to that, you can make a thruster out of a single ion emitter, or you can cluster these ion emitters and create large arrays of arbitrary numbers of individual emitter tips combined, and you can tailor those arrays to some specific use case. So many different shapes and sizes can be manufactured, which makes electrospray thrusters uniquely scalable. And then one last point on electrosprays in general is that they often make use of MEMS or micro electromechanical systems manufacturing. And it's really advances in these MEMS manufacturing techniques that has in recent times allowed and enabled fabrication of higher quality and higher density emitter arrays, which allows you to produce more thrust in a smaller footprint. And that's really the topic of the product that I'll be talking about today is higher density arrays. So continuing on, first of all, the state of the art with electrospray thrusters, for example, electrospray ion thrusters that have flown on orbit and are currently operating on orbit, typically use some kind of porous substrate. So for example, a porous metal or more recently porous glass. And these substrates are typically laser ablated to form conical emitters. The primary innovation that we are working on in this program is the use of silicon as an emitter substrate material. And this allows us to take advantage of some pretty enormous capability in the silicon MEMS manufacturing arena. So primarily, the use of silicon emitters enables, first of all, mass production using MEMS manufacturing infrastructure that already exists. So instead of fabricating, say, one of these emitter arrays at a time, they can be produced with relative ease in batches of hundreds or even thousands at a time, just like a semiconductor chip for the electronics industry. And in addition to the mass production capabilities, we can achieve through silicon MEMS manufacturing much more complex, higher resolution, and perhaps most importantly, repeatable structures in silicon. And this really enhances or has the potential to enhance the performance of the devices because the geometry of these emitter tips is a real driver for many of the key performance metrics. And then finally, I'll highlight this diagram in the bottom left, which is kind of a cartoon of the technology that we're working to develop. And you can see the emitter substrate material below the extractor electrode. It has a combination of conical tips and capillaries that go through the substrate surface to the backside, which allows it to connect to an external fuel reservoir. And this is something that we've developed specifically so that we can passively feed these emitter arrays and allow them to fire with passive replenishment, which is, as we'll see based on the testing results, a really key driver for what makes these thrusters kind of unique. So continuing on, I want to highlight some of the more important test results that we've achieved from the development of these silicon emitters over the past year or so. So first, and perhaps most importantly, we've been able to achieve and repeat a stable ion emission from these emitters in the pure ionic regime using this passively fed propellant system. And this is important because while silicon electrospray ion emitters have been researched before, the ability to fire them in the pure ionic regime, so meaning that pretty much all of the species emerging from the thruster are pure ions rather than charged liquid droplets or something like that. So the ability to achieve emission in the pure ionic regime through passive fluid transport from an external reservoir is believed to be new for silicon thrusters. And this really showcases the innovation of the combined tip capillary architecture made possible by using those silicon MEMS manufacturing techniques. So after demonstrating the ability to fire a complete thruster unit, we used several common, are still using several common methods to characterize the thruster and its ion beam. So these include common techniques such as taking a current voltage characteristic response, measuring the angular beam distribution, using time of flight mass spectrometry, as well as retarding potential analysis, or RPA. So showcased here is not all of those, but a couple of examples. So for example, to the left is one of the first current voltage response curves taken from one of these devices. And on the right is a beam mass spectrum acquired through time of flight mass spectrometry. So on the left, the current voltage curve, among other things, it shows the ability of the thruster to start up and operate below 1000 volts, which was a kind of a key requirement for this program, as these thrusters are meant for very, very small and power limited systems. So the ability to operate at these low voltages and low powers is really key. And then to highlight the time of flight mass spectrum on the right, this really shows the distribution of ion masses that are present in the ion beam that's emitted from the thruster. So now is also a good time to talk a little bit about the propellant that we use. As I mentioned, we use ionic liquids, and specifically for this program, we've been focusing on the ionic liquid EMI BF4, which is, ionic liquids are pretty much a liquid salt. So it's a sea of positive EMI plus cations and negative BF4 minus anions. And we expect to see these species present in the ion beam, of course, depending on which polarity we are operating in. So noticeable spikes on this time of flight spectrum occur at masses corresponding to the mass of a single EMI plus ion. Another spike at a mass corresponding to an EMI ion attached to a neutral particle, and another small bump at the mass corresponding to an EMI ion attached to two neutral particles. And then we see, additional larger clusters making up a small percent of the ion beam. So from the mass spectrum, we see that in this specific case, the beam is comprised of about 80% of those monomers, maybe 15% of those dimers, and a small percent, 5 or less, of those larger clusters with maybe some very small charge droplets. So these are fairly promising ion beam characteristics for this thruster, considering we see 99+% of ions being emitted from the thruster. And an additional topic that I'd like to discuss is some of the additional testing that we've done and demonstrations that we've performed in the Space Propulsion Lab to illustrate pretty much these thrusters' ability to operate in representative environments to prepare for eventually an orbital flight test. So shown here is the magnetically levitated thrust stand in the Space Propulsion Lab. So like a torsional pendulum thrust stand, thrust on this maglev stand is measured by tracking the response of the system to torques induced by the thrusters. Unique about the maglev stand, however, is that it is completely free from contact to any other part of the chamber or facilities. So a test CubeSat is levitated such that it is free to rotate about a single axis, and it is free to rotate a full 360 degrees around that axis. So the thrusters, in this case, a pair of thrusters, are mounted on the CubeSat where these white squares are, such that they produce a torque about this axis. And what I'll show now is a video of a pair of these silicon-based thrusters operating on the maglev test stand. So the video starts right now with the thrusters off, and the satellite is oscillating naturally. When the thrusters are commanded to fire, which will be seen in the video, you'll see the satellite break free from this natural oscillation and begin to accelerate in a single direction. So that is what is starting to happen right now. This demonstration serves as a proof of concept for a couple of key objectives in this program. For one, we were able to obtain a direct thrust measurement based mainly on the change in the angular velocity of the satellite over time, which in this, for this specific test was pretty much perfectly linear as you'd expect from a constant thrust system. We're also able to demonstrate the ability to remotely operate these thrusters on a flight-like power processing unit, or PPU, using radio communications, because as I said, the satellite, when it's levitating, is completely free from any connections, electrical or otherwise, to the rest of the facilities. And another thing to note is that no external neutralizer is needed for this system, as we're able to operate the two thrusters in opposite polarities. So one producing positive ions, the other producing negative ions. And we're able to ensure that equal but opposite currents are being emitted from both, which is really another advantage of electrospray propulsion, and it makes it a good candidate for a lot of different types of missions. So to kind of conclude here, I'll just summarize quickly the main points, which many of these are topics that I've already discussed, but really what I'd like to highlight is the fact that the novelty of these devices is that they're manufactured from silicon, and this enables not only the fabrication of really large numbers of emitter arrays with record-breaking densities, but it also allows us to pack more of these emitter tips into a smaller space and increase the thrust density of electrospray thrusters. So our initial characterizations of these emitters integrated into a thruster have been really promising. As I discussed before, we've demonstrated that they're capable of operating in a useful way. So we see that they produce thrust and can move a satellite on a vacuum chamber in the ground. And they are also capable of operating under the size, weight, and power constraints of very small systems. And then we've also shown that self-neutralizing pairs of thrusters are possible, which make them a really good candidate for a really wide variety of missions, from low Earth orbit all the way to deep space. So there's still a lot of work that we're doing on these emitters to put them in a configuration where we can put them on a satellite and do an orbital flight demonstration. But we do hope to be at that point soon, and eventually be using these thrusters to power a lot of different types of missions. So thank you for listening, and please feel free to ask any questions, and I'll be happy to answer.
So thank you very much for this very, very good presentation. So if we have some questions, this is the moment.
Yes, Finn, please.
Yes, you can speak if you want.
Thank you. I have a question regarding the startup of the emitters. So did you repeatedly start and stop the emission, or are you just like firing and then going on? Because in literature, there are reported differences between voltage-based and fluid-based startups. For example, if you start the voltage before the fluid is supplied, and if you supply the fluid before the voltage is applied, do you see any differences?
Yeah, good question. So these, as I mentioned, the emitters are passively wetted through capillary action. So we really need to get the hydraulic impedance of the system. So from the fluid tank to the thruster face, pretty much perfect for them to operate correctly. But when we have that hydraulic impedance correct, which we believe we've achieved, the emitters become conformally wetted such that they are wet before voltage is applied, and once we turn them on, it starts emitting, and more propellant is drawn to that surface as propellant is depleted and expelled from the thruster. And like I said, as long as we have that hydraulic impedance correct, we can sustain that until some other failure mechanism breaks the thruster hundreds of hours, hopefully tens of thousands of hours later, eventually. But for now, we are able to start up and stop the thrusters as we wish. We've even been able to, test a thruster and take it out of vacuum and refill it and put it back in the chamber and continue to fire it. So we've done things like that.
Okay, may I ask a following question?
Absolutely.
Sure.
Do you think your hydraulic balance is broken if the satellite is placed into the gravity-less space? So if, for example, does the gravity affect the hydraulic balance of your system?
So if I understand the question correctly, you're asking about the gravity effect on the hydraulic impedance. And the answer to that is that based on pretty much any model that you can create, gravity should have pretty much negligible effect on the draw of the propellant. It is interesting because not a lot of, obviously hard data is available for this. There have been electron spray thrusters that have flown in space, but not a lot of public data is available. So that's something that we hope to change as well. And that's why we're looking to do a flight demonstration in the next 2 to 3 years. But it's a really good question. So I think we believe the answer is it shouldn't have an effect, but of course, no one can really say that until we prove it. So we're looking to prove that.
Thank you very much.
Yep. I see a question in the Q&A. Could you remember us? What is the efficiency of the thruster? Yeah, so thank you for your question. The efficiency, I opted to not put a lot of performance metrics in this presentation, and instead opted to kind of focus on those couple of characterizations of the emitters specifically, mostly because we are rapidly iterating on the design right now. So just in the past year, we've gone through several iterations of the emitter design, and we are closing in on a configuration of the thrusters that we'll be able to put together and ship off for a flight test. But right now, we are really focusing on perfecting the emitters, and we could do a efficiency calculation, of course, based on the thrust measurements that we've taken and the power that we were consuming. I don't have that number, unfortunately, but really we're still focusing on figuring out what the device will look like and what the product will look like, because we're still pretty early on in the life cycle of these devices.
Thank you for your answer. But it's just for improvement, you know, for possible improvement. It's good to know what is the current efficiency so that we can see from where it's coming and so on. Okay, thank you.
Yep, thank you.
Okay, thank you very much, Matthew, for this presentation. So we can finish here this session number 2.
Yeah.
And we have a break now, and we can see.
We start again at 4:40.
Yes, we can. You can start again at 4:40 p.m. Yes.
Yeah. Alberto, please.
Yeah.
Yeah. Put me animateur.
Yes, sure.
Yes. Thank you.
Thank you very much.
Thank you. Merci, Alberto.
Merci. Je te laisse la main alors, Laurent.
Oui. Ok, je termine. Par contre,
Okay.
j'ai toujours pas les personnes a priori qui doivent parler. Mais bon.
Ils sont pas encore là.
Non.
Si j'ai bien compris, non, mais ils vont.
Oui, d'accord.
Ouais.
Bon,
super.
Bravo.
Ouais, merci, bravo à toi aussi. Merci beaucoup.
Allez, à plus.
À plus. Ciao, ciao.
Ciao. Valentin, are you here?
Yes.
Yes. Okay. Fine.
Yep.
So we wait 2 minutes. Okay.
Can you hear me well?
Yeah. Yeah. Very well.
Cool. Thanks. I'll start to share my screen.
Yeah.
That's okay.
Yeah, you can do it. Yeah, all right.
Everything's fine?
Yeah. Yeah. Yeah.
Okay.
Okay, so I think that we can start again. So my name is Laurent Garrigue. I'm a research scientist at the CNRS at the University of Toulouse, at the Laplace Laboratory, and I will be a chairman of the last part of the first day of the workshop. And we will start with a presentation of Valentin Hugonneau, who will talk about ion current and ion energy measurements, dual mode electrostatic probe development. So please, Valentin, it's up to you.
Thank you. Good afternoon, everyone. So I'm going to talk about the work that has been done at Impulsion and the CNRS on the development of the dual mode electrostatic probe to measure the ion current and ion energy of a FIB-based technology. So the idea was to merge two different well-known probes, so a Faraday cup and an RPA, into one, to basically ease the probe implementation into a small vacuum chamber to decrease probe design complexity, like for the RPA, which needs quite a lot of grid, to provide different ion information for the same plasma condition, but also at the same location, and also to enable better plume characterization for electric propulsion system in the case of massive production. So I will divide this presentation in 3 parts. The first part will be, I will show you the development and the working principle of the single probes, a Faraday cup and a RPA. Then I will discuss with you about the dual mode concept, and I will present the experimental results that we obtained. And finally, I will compare all those results. I will go quite fast on this slide, since you had an introduction by Tony earlier. The ion source studied here is a FIB-based technology. It's the Impulsion Nano Laboratory Unit. So just few key characteristics. It's the propellant used is indium. The energy of the ions are believed to be from 2 to 10 kiloelectrovolts. The current density are quite low, at least for this study. The ion current is known and controlled, and theoretically we assume to have the ion energy should be the same that the potential applied to the emitter voltage. The emitter here is on the bottom right of the slide, is basically composed of the crown and the tank. When the indium is melted, it goes to the tip of the crown, and then by applying a strong discharge voltage between the extractor and the emitter, you extract the ions, eject them, and accelerate them, which create the thrust. On the bottom left, you have a sketch of the crown that we used for the study. So we had 24 injectors out of 28 firing. So we assume that the beam is homogeneous and symmetrical. So the probes that we developed as a single probe were RPA. The design was based on the recommendation made by Fotec a few years ago at the APC. And the Faraday cup was developed by Impulsion and the CNRS. And the optimum design was found to study the beam, the ion beam of a FIB thruster. So for the Faraday cup, on the left side, you see the current ion current density distribution of the ion beam. And by doing the integration under this curve, we are able to measure the whole ion current. You can see on the right side the blue dots are the ion current retrieved by the Faraday cup, and the red square are the known current, the one controlled. We have an overall absolute deviation of 2% from between the measured and the known current. Regarding the single probe RPA, we tested the RPA with different emission voltage and also emission current, and we saw that there were no effects on the output. Actually, we saw that the maximum measured ion energy that we have with the RPA corresponds quite linearly to the emitter voltage applied to the thruster. So now that we have two working concepts, I will talk about the dual mode one. So there are a few design and technical requirements for the development of this probe. First was to minimize the plasma perturbation. So we had some restriction on the probe size to have a measurement system as simple as possible. So not a lot of electrode inside the cup, and also keeping accurate ion current and energy measurements. So when the probe is used as Faraday cup, we should try to recollect as much secondary electron as possible. So on the right side, you can see the dual mode concept operated as a Faraday cup or RPA. So when it's operated as a Faraday cup, you can see two electrodes. So the repeller, which is the gray electrode here, is biased negatively to repel all electrons to go inside the probe, and also to recollect secondary electrons emitted by the collector in red here. So we are sure that we are collecting the right ion currents. When we operate the probe as an RPA, we uncouple the cup in two electrodes. The collector becomes just a disc at the bottom, and then the wall of the cup becomes the ion screener that we will bias positively to screen all ions. One issue with the RPA, the grideless RPA, so when we use the probe as a RPA, we will not be able to recollect the secondary electrons unless we add a third electrode. But this would be against some of our requirements, which would be the length and the simplicity of the design. Or we can measure the secondary electron yield applied for the collector material, which is here in this case tungsten. Since it was not available in the literature, we did the measurements ourselves, and now we had the value here. We conducted some ion trajectory analysis to see if with the software SIMION to see if the concept was working. It seems to work theoretically. We see that with design, we have the feed lines that you can see here are a little bit going outside the probe, but the feed lines that reach the outside are very low, like from 5 to 10 to 20 volts. Which is this can be negligible, considering that we are dealing with kilo electron volts ion energy. The ion screener length here that you can see here was decided to be 30 millimeter. It was basically a trade-off between the overall dimension of the probe, but also the dimension of the ion screener that where we can apply a potential not too high to screen all ions. In this case, by just applying more or less the same potential than on the emitter voltage, we are able to screen all the ions. We wanted to try two different diameters for the ion screener. So one would be 9 millimeter, which is, in this case, that would mean that the ion screener will be the same diameter than the repeater, and one is 13 millimeter. So we have an ion screener a little bit wider. We wanted to see as well if the probe will be able to deal with primary electrons and not just ion beam. And it seems that the case when we apply a strong enough potential on the repeater here. And finally, also the secondary electron, in the case that we add this third electrode, we see that as soon as we apply different potential way lower than the collector, we see that all secondary electrons are properly recollected. So we started directly with this design where all the electrodes are here, and we use the probe as the RPA. You can see here that's the current density for different cup voltage or in different emission voltage. And we see that when we apply the secondary electron electrode, we're connecting properly the secondary electrons, as we can see here. Because when all ions are completely screened, we have no signal here, while when we are not using this electrode, the secondary electron, we are still having a signal here, even though the ions are completely repelled. This is due to the fact that in the cup, there is still some neutrals remaining here, and they are reaching the collector, emitting the secondary electrons. Now the idea is to make the current density less unstable. So we try to reduce the repeller thickness and have just a disk instead of a big block. And we see that it has an impact and we have something more stable. However, we see that when we look at the second plot here, we see that the energy distribution is shifting toward lower energy. And also as we increase the emission voltage, but also we see that the energy distribution is growing. We believe that it is due to the fact that because of the length of the ion screener and the diameter, ions are colliding and create virtual electrodes that shift the ions toward lower energy. So we try to increase the diameter of the ion screener. We increase it by 4 millimeters. And we see that it's working and it has an impact that the current density here is way more stable. And we have no more dependency of the ion energy shift with the emission voltage. Also no more broadening of the energy distribution. We still have an energy shift of around 3%, but this is constant all over for all thruster operation. Then we wanted to try if there were any influence of just changing the bias on the collector and the repeller. It seems that for the collector, obviously there is none as long as the collector is negatively biased, and for the repeller, as long as this one is either floating or negatively biased, we have no impact on the signal, on the energy shift. Then we did some measurements with the different ion current, with different emitter current, emission currents, so from 1 to 4 milliamp, and we see that there is no impact on the change of current density on the energy measured. And also we tried a different location of the beam profile. And since it's a FIB-based technology, we expect to have an ion energy to be equal all over the beam profile, which is the case here. So we have no influence on the probe measurements. Finally, for the RPA mode, we tried to see what would happen if we insert some electrons inside the system. So what we did is we wanted to know the potential to apply to the repeller to make sure that the current that we measure on the collector is the same than when we are not having any electrons. We tried different repeller and we see that -400, all electrons are completely repelled, and we have exactly the same current density as when we are not having any electron on. So when we switch to RPA mode, we see that there is no impact neither when we keep the same potential on the repeller, so -400. So we repel all electrons. We see that there is no impact here on the energy shift. It's more or less 3%, which was the case for the other data points. And finally, we tried this the probe as a Faraday cup, and the Faraday cup is also seems to work as well. However, we are measuring a little bit higher current density, a few percent, but this is as well a constant for every thruster operation. And so this is something that we can adapt and readjust. So to conclude, we showed that the dual mode concept was feasible for feed thruster technology. When we use the dual mode as a Faraday cup, we have more an offset of plus 4% on the ion current that we measure. We believe this is due to the incomplete secondary electron recollection. And for when we use the dual mode as a RPA, we have an offset of 3%, which is due to the length of the distance between the collector and the ion screener. So with this probe, we have the possibility for a given plasma condition to measure the ion current density regular distribution, then the ion current, the ion energy distribution for different kiloelectrovolt ion energy. And with these two data, we are able to compute and determine and derive the beam divergence, for example, the deviation, but also to measure indirectly the thrust. Thank you.
Thank you, Valentin, for your interesting talk. So now your talk is open for discussion. Any comment, any question, please, in the audience? Maybe I can start. When I see your calculation, right? When you show your calculation about trajectory, you basically assume that there is no plasma, okay, inside your system. So it depends what is the Debye length. I mean, what is the ratio? I would say the Debye length and your typical size of your system, of your probe. So I saw that it was typically in the order of 1 centimeter, right? Your probe is on the order of 1 centimeter in length, or
in length, it's more or less 7 centimeter.
7 centimeter, okay. Yeah. And so the question is, have you some estimation of plasma density? I mean, when you apply for a real system, have you some order of magnitude of plasma density in the plume at the position where you do the measurements?
You mean here, like in this case, where?
Yeah.
So it's few microns. What I was measuring like 30 centimeter away from the thruster. Yeah. So it's a few microns per square centimeter. But I know that if we go to 100 centimeters, so more or less 1 meter, it goes down to nanoamp per square centimeter.
Okay, so you mean that your plasma density is very low?
Yeah, we have very low plasma density. So the Debye length is, I haven't done any computation, but I think it's around a few like centimeters.
Can you say it again, please? Because there is one comment about that also in the discussion panel. Yes, please, can you repeat the dimension of a probe and what is the Debye length?
The Debye length, I haven't done any computation on that or any measurements with the planar probe, but I believe it's around a few centimeters since it considering the plasma density here.
Yeah.
And the overall of the probe, the dimension of the probe is 7 centimeters.
That, I mean, yeah, that was a question in the panel discussion. Yeah. My colleague, so Yevgeny Raidzes, talk about the orifice.
So the inlet here, it's 7 millimeters.
7 millimeters. Okay.
We've conducted few analyses that you can find here in this paper. Okay. Where we changed the orifice here, which went from 1 to 7 millimeters. And we saw that the optimum was 7 millimeters. You can more information there.
Okay. Other comments? This question, please. Okay, so I will continue maybe to ask the last question. Maybe, yes, can you come back, please, on your typical distribution function in your I was wondering if you can see some, some structure in the tail. I mean, for example, multi-charge ion or these kind of things. It seems not. It seems that you have only one beam of one given charge ion. Is it correct?
It's I guess you're referencing also to oil thrusters or stuff like that.
Yeah.
In this case, it's really one pure ion beam. There is no charge exchange. I mean, even in the current density, we don't really see these wings that we can observe in oil thrusters.
Okay. Thank you. Other question, comment? Okay, so if not, we can thank again the speaker. Thank you, Valentin.
Thank you very much.
Nice presentation. Bye.
Thank you. Bye.
So now the last presentation is from Ethan Opping, but I did not see it. I did not see him in the list of participants, so I'm checking again if I see him in the maybe in the spectator, in the panelist. No, I did not see him. What about in the list of? No. He's not connected. No, so he's not connected. So I think that we can wait maybe two or 3 minutes. Yeah, we can wait a bit, just waiting for his connection eventually. So I think that Ethan Opping is not here. So I think that we can close the session. Okay, so thanks for all the speakers of today. And so see you tomorrow morning, and we start at 9:20 by a talk of the Trust Me company. Okay, guys. So I said so. Bye bye, and see you tomorrow. Bye.
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 Goodbye.
Bye. Marlène?